my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Welcome everyone to another session of Maths Hub, where we deal with everything maths and science, grade 11 and grade 12. Now in this segment we are going to deal with grade 12 vertical projectile motion in 1D. Now, as you saw in that small segment, in that small introduction at the beginning, that astronaut is David Scott, who actually demonstrated what we are going to deal with today, which is free falling bodies. Free falling bodies is an ideal situation where air resistance is ignored. Now, if air resistance is ignored, it means our acceleration will essentially become constant. Now what he did is he held the hammer and the feather at the same height, dropped them, and what actually happened is they reached the ground at the same time. Now can you imagine that? If you try to do that here, and now you go outside, you get a hammer and you get a feather and you drop them, the hammer will actually reach the ground much faster. Now why is that? Now the moon actually, since we have an atmosphere, and in the moon there's actually very thin air, or there's little air resistance, hence the feather and the hammer managed to reach the ground at the same time. That's actually what we are going to deal with. We are going to deal with vertical projectile motion. Now let's get going with a few definitions. Now the first one, we are going to try to understand these concepts and definitions. The first one is it's actually a definition of vertical projectile motion, which is a motion of objects that are moving upwards or downwards while experiencing a force due to gravity. Now, in that ideal situation where air resistance is ignored, remember, we are drawn towards the center of the earth. Now, what is drawing us towards the center of the earth is actually the force of gravity, right? Now, each and everything that we are going to deal with, we are going to ignore air resistance. Now, in ignoring air resistance, it means our gravitational pull becomes constant. And I think you know this by now, that our gravitational pull is 9.8 meters per second squared, right? Now that is basically what we are going to do today. So let's start. Now moving on to the next concept, or the next important part, is we describe what is projectile. A projectile is actually a body or a particle that is projected or launched and then moves under the influence of only gravity. Like I said, guys, we are drawn towards the center of the earth, right? Now the gravity is pulling us towards the center of the earth. That is basically what a projectile is. Now we are thankful for that, because we wouldn't be standing as we are standing, we will be floating. And actually, the further you move away from the center of the earth, the less the gravitational pull you'll experience, right? Now let's move on to our next concept. These are the key concepts that actually will get us going. The first one is gravitational acceleration is always towards the center of the earth and it is constant. Now what makes it constant is, like I said, in an ideal situation is constant when we neglect the air resistance, right? Now projectiles that have an initial velocity upwards will have zero velocity at their greatest height. Now trying to explain this, if let's say you throw a ball up, right, there will come a point where this ball that you've thrown up will actually come down. Now at that instant, as it goes up and then it changes direction and then it moves down, that instant your velocity will be zero. Your velocity will be zero, right? Now another key concept, another key term that you guys need to understand is time symmetry. The time that it takes for the object to fall back down to height h is the same time taken for the object to reach its maximum height. Now remember, there's this saying that what goes up must come down, right? Now this is basically it. Whenever, if you throw an object up and then it eventually comes down, in that the time of that upward motion will actually equal the time of the downward motion. That's time symmetry. If it takes 2 seconds to go up, it will take 2 seconds to go down. All right? Moving on. Now guys, for us to understand these projectile motion, you need to go back and revise your grade 10 graphs of motion. Now we are going to talk a little bit about that and do a little bit of revision. Remember, in grade 10 you did the position versus time graph, you did the velocity versus time graph, and then you did the acceleration versus time graph. Let's refresh your mind by just going through those 3 graphs that describe the motion. Now the first type of motion that we are going to explain is uniform. It's uniform motion. Uniform motion or constant velocity. Constant velocity. Velocity. Let me just write it in short so that we save ourselves some time. Now, if we look at this type of graph where an object travels at constant speed, let me quickly get my ruler in the right position. Let me get it in the right position. All right, it's fine. Now the first one that we are going to cover is position versus time. We are going to do position versus time. change in x versus time. Now you know always on the vertical axis what you have, you always have time, which is measured in seconds, and then on the vertical axis you have your change in position, which is measured in meters, where position, which is measured in meters, this is going to be our first graph. Now if the position starts from 0 and we are traveling at constant speed, let me just rewrite it. This would be our position versus time graph. Now, does it make sense if you look at it? Does it make sense? Of course it makes sense, because if you are traveling at constant speed, you will increase the amount of meters that you travel as time goes by, right? As time goes by. So this is our position versus time graph. And going to the next one, we will have velocity versus time graph. Let me just try to write it down here. Velocity versus time graph. This will be my velocity versus time graph. Again, this is time, which is measured in seconds, and then here we have velocity, which is measured in meters per second. Now this graph, if you're traveling at constant velocity, meaning your speed doesn't change, right? It will basically give you a straight line right across. And then looking at our last one, which is acceleration versus time graph. Guys, this is grade 10's work, so this is purely for revision and to refresh your mind's purposes, right? Now here we have acceleration, which is measured in meters per second squared, and then here we have time, which is measured in seconds. Now in this case, if you travel at constant velocity, it basically means your acceleration won't change. It will stay at the same place and it won't change, right? Now another form of motion, which is represented graphically, it would be motion with constant acceleration, with constant acceleration. Right? So in this case, we will have this sort of graph. Now this one is going to be position versus time, and remember again, this is time in seconds, and then this is our position, right? Now guys, if you accelerate, right, it's going to take you from the beginning, it's going to take you less time, right, to cover a certain distance. Now as you move along, you will still cover less time, but then your graph will sort of like it's getting towards the inside. Let me just write it down so that it can be clearer to you guys. Now as you accelerate, it will take you less time to cover a certain distance. Right? Let me just try. I'm trying to start from 0, but my writing actually isn't up to scratch. Now this would be our displacement versus time graph, right? Now as you can see, it takes less time and then to cover a certain distance, and then it goes up, it goes up, it goes up, and then you still cover a certain distance when you accelerate, but then remember the acceleration is constant, right? Now moving on to our next graph, which is velocity versus time graph. Which is the velocity versus time graph. Again, it's time in seconds. Here we have velocity in meters per second, right? Now if you are moving at constant acceleration, right, if you're moving at constant acceleration, it means you are constantly increasing your speed, right? And this would be our velocity versus time graph. This is the velocity versus time, right? Now moving on to the last one, which is acceleration versus time. Acceleration versus time. Again, we have t in seconds, and then here we are going to have acceleration in meters per second, in meters per second squared. Now, if you are traveling at constant acceleration, it basically means it doesn't change, it stays there, right? Meaning, as you move, your acceleration won't be changing, it would be constant, right? This is our acceleration versus time graph. So that's basically a short revision or short summary of your graphs in terms of motion for grade 10. Remember, I started by saying in an ideal situation, our acceleration is constant, right? Now, in helping us dealing with this type of situations where motion actually is carried out in where we neglect air resistance, there are formulas that we use that we call equations of motion. And these equations of motions, you can apply them only when you're dealing with constant acceleration. Now, looking at these equations of motions or equations of kinematics, right? The first one that we have is Vf equals Vi plus At. The second one, we will have change in displacement equals Vi plus Vf over 2 times T. Third one, the third one would be a change in displacement equals Vi times T plus half At squared. And then the last one would be Vf equals Vf squared, actually Vf squared equals Vi squared plus 2a times the change in displacement. Now remember, our Vf is what? It's our final velocity, and then our Vi is our initial velocity, and then our A is our force of gravity, which is constant at 9.8 meters per second squared. And then we have our change in position. This will be our position, This will be our position. Now guys, can you identify for me in those equations which are vectors and which are scalars, right? Remember, it's very important to know each and every variable, right? It's very important to know each and every variable. Now, like I said, this is our final velocity, which is a vector. Now a vector, remember, if you're dealing with vectors, you need to have a magnitude and the direction of whatever you're dealing with, right? And then the second one is the initial velocity, and then we have gravity, and then we have position, and then last one would be time. Now in these first four, they are vectors. So whenever you calculate these, you need to include what? You need to include your direction. Now we include direction in these vectors by basically choosing remember, we're dealing with only upwards and downwards motion. So you need to, whenever you solve this, you need to show by a form of a sign, a negative or positive, whether you choose the upwards direction as positive or you choose the downwards direction as negative, right? But acceleration is always moving, it's always towards the ground, right? So acceleration is always negative. It's always negative because it's towards the what? It's towards the ground. So ideally, our acceleration or our gravity will always be negative 9.8 meters per second, right? Now let's look at our first example, which says a bullet is shot straight upwards from a gun. Now the following graph is drawn, right? And then it continues to say downwards was chosen as positive, which is very important, guys. Like I said, the sign that you choose, whether positive or negative, will determine the direction of your vectors, which are acceleration, velocity, and displacement, right? Now in this case, they say downwards was chosen as positive. Now from the graph, they say describe the motion of the bullet. Right? Now if downwards was chosen as a positive, it means whatever goes up would be negative, right? Now from the graph, you can see it starts, this is a velocity time graph, right? You see it starts at minus 200 meters per second, which is the initial velocity of the bullet, right? And then it gradually increases, right? It gradually goes up, right? Now if you try to describe the motion of the bullet, you would essentially say the bullet moves at a decreasing velocity, right? At a decreasing velocity upwards for how long? For 20.4 seconds, right? So it goes straight up, and then as it goes up, it keeps on decreasing its velocity, right? Up until 20.4 seconds. Can you see from 20.4 seconds, your velocity is 0, because you can see here it lies on 0 meters per second. That's where the bullet stops momentarily before it does what? It drops back, right? Now it drops back for another 20.4 seconds. Why do I say that? Can you see it goes, as it drops, it again maintains its speed of what? 200 meters per second, right? Now as it comes down, it will drop and it will reach the ground or the initial position at exactly the same time, because if you add 20.4 and add another 20.4, it will give you 40.8 seconds, which is what I explained earlier on, which is what? Time symmetry, right? So the amount of time it took the bullet to go up, it will take exactly the same time for the bullet to go back to its original height or original position, right? So that's basically how I would describe the motion of the bullet. It goes up as it gets shot, and then as it moves up, it decreases its velocity, because remember it's getting pulled by gravity, right? So it won't be moving faster and faster as it goes up. It's going to decrease, and then at some point here at 0, it will stop and then start moving down at the same time it took for the bullet to go up, and then the instant it returns to the ground, those times are equal, which is what I said is what? Our time symmetry. Now moving on, it says draw a displacement time graph. It says draw a displacement time graph. Now if we are going to draw a displacement time graph, what is missing from that? And what is also important, guys, whenever you're dealing with equations of motions, right, what you need to actually get around is you must get 3 variables. That's when you can actually solve equations of motions, right? If you have 3 variables and you have one unknown, you can easily get the other one, right? So here they want us to draw a displacement time graph. Now, do we know the maximum height where the bullet actually started turning and started moving down? We don't know. So they are looking for, we need to determine our maximum height first, right? We need to determine our position, right? The position of the bullet. Now we actually need to calculate that before we start, right? Now what do we know from the question, right? Let's start there. What we know is our acceleration. Now remember they said downwards was chosen as positive, meaning our acceleration will be 9.8 meters per second squared, right? And then what else do we know from the question? Let's go back to our graph and see what we can gather from our graph. We know the bullet was traveling at 200 meters per second, right? So that is our initial velocity, right? Which is 200 meters per second, right? Now what is missing from that? Of course, we are missing the direction of our velocity. We are missing the direction of our velocity. Now, is it moving up or down? It is moving up, but then they asked us, they said we must choose the downward position as what? As positive, meaning our initial velocity will be negative 200 meters per second, right? And what do we know again? Let's go back to our graph. What do we know? We know it took the bullet 20.4 seconds to reach its maximum height, right? So we know the time, which is 20.4 seconds. All right, and we actually know our final velocity at maximum height as well, which is 0 meters per second squared per second. Now going back to equations of motion, I will choose this one. A change in x equals initial velocity plus the final velocity over 2 times t, right? Remember I said we know our initial velocity, which is 200 meters per second, plus our final velocity, which is 0 all over 2 times our time, which is 20.4 seconds. Now 200 divided by 2, it will give me 100 times 20.4, it will give me 2040 meters, right? 2040 meters. Now from this, after calculating your displacement, you can easily draw your graph. So let's go about in drawing our graph. Let's go about in drawing our graph. Now from here, remember, this is our displacement, which is in meters. This is our time, which is in seconds, right? So we are going to have 0 here. So let me see if I can write it according to scale. Alright, I'm just gonna do it roughly, but then I'll try to be as accurate as possible, right? So I'm gonna go with a scale of 10, 20, 30, 40, 50, let's say 60. And then here I'm gonna go with 500, and then say 1000, and then say here 1500, and then say here 2000, right? So remember I said here it's 10, 20, 30, 40 and 50, and then here we have 60, right? Now what did we get for our displacement? So 20,40 would be right about there. I'm actually too high. It will be, well, then it's fine. Let's just put it there, right? And then let's go back to our graph. Let's go back to our graph, right? Now it started from, in terms of displacement, it started from 0, right? And then it went up to 2040 meters, right? Let's go back to, let's get back to our graph again. It went up to 2040 meters for how long? For 20,4 seconds. So I'll just plot it here. Let's say this is 2040 meters, and then 20,4 seconds would be around about here. And then what happened again? This is our maximum height. And then after reaching this maximum height, it started dropping again, right? Now as it dropped, it's gonna take it the same time as it went up, right? Which is double the time, right? Which will be 40,8. So I'll say it's around about here. So let's plot our graph. Oopsie. I'll say it's around about there, right? So let's plot our graph. It will go something like this. It will go up, and then it's going to reach its maximum height at 2040, and then it's going to start dropping, and then it's going to start dropping until it reaches its original height at the time of 40,8 seconds. So this is basically how we would sketch our graph. It's a rough sketch, but then this is basically what we would be doing, right? So moving on to the next question. The next question, what they're asking us to do is draw an acceleration time graph. Acceleration time graph. Again, let me get my ruler. There you go. Now again we have 10. All right, let me just label my graph. This is time, this is my acceleration in meters per second squared, and then we will have 10, 20, 30, and then 40, and then here we will have, let's say 2, 4, 6, 8, 10, right? Now guys, remember, acceleration in an ideal situation is what? 9.8 meters per second squared, and it's what? Constant, right? Meaning I would put my 9.8 roundabout here and write a straight line across, which would be my 9.8 meters per second squared. Excuse the line, it's not that straight, but then if I draw it with a ruler it would be straight, but I'm sure you guys get the idea. So this would be our acceleration versus time graph. Now let's move on to our next example, which comes from the November 2017 paper. Yeah, question 3, which deals with exactly what we are doing today. Now it says stone A is projected vertically upwards at a speed of 12 meters per second from height h above the ground. Now ignore the effects of air resistance. It says calculate the time for stone A to reach its maximum height. That's our first question, right? Again, where do you start? You start by writing down your unknowns and giving them direction, right? How do you give them direction? By assigning a plus or a negative sign to your variables, right? Now let's choose the upwards direction as positive, right? Now our gravity would be negative 9.8 meters per second squared meters per second squared. What else do we know there? We know our initial velocity, which is 12. Let me just do this. We know our initial velocity, which is 12 meters per second. And then what do we know again? We know our final velocity, which is 0 meters per second squared. Why do I say 0 meters per second squared? Let's reread the question again. The question says calculate the time taken for stone A to reach its maximum height. Now what happens at maximum height, right? Remember the initial velocity is 12 meters per second, right? Maximum height, that's where instantaneously the stone stops before it starts to drop down, right? Now that moment where it stops, the velocity becomes what? Becomes 0, right? Hence we have our final velocity there. Now I'm going to choose V final equals V initial plus AT. Remember, we are looking for what? We are looking for time. Now our V final is what? Is 0. Our V initial is 12 plus our acceleration is minus 9.8. We are looking for time. Now if I take my 12 across is going to be negative 12 equals negative 9.8 t. If you divide everything by 9,8, you will get, by negative 9,8, you will get a time of 1,2 seconds. Now it took stone A to reach its maximum height in a time of 1,2 seconds. This is question 3.1, right? This is 3.1. Let's go to 3.2. Let's go to 3.2. Let me just quickly go back and read the statement. It says, at the same instant that stone A is projected upwards, right, stone B is thrown vertically downwards from the same height at an unknown speed v, right? They say you must refer to the diagram below. This is the unknown speed of stone B. Now it continues to say, when stone A reaches its maximum height, stone B is 3v, right, which is the speed, right, which is the speed. Now they say calculate the speed with which stone B is thrown downwards, right, which is, you need to calculate the initial velocity of stone B. You need to calculate the initial velocity of stone B. So let's tackle that. Let's quickly tackle that. Right, what do we know? We know our time, which is 1,2 seconds. Because why? Because when stone, they say when stone A reaches its maximum height, the speed of stone B is 3v, right? 3v, which is what we are trying to calculate here. And then we have our acceleration, which is negative 9,8 meters per second. Now at the same time, right, at the same time, concurrently, as stone A reaches its maximum height, we have our final velocity for B, which is 3v, right? And then its initial velocity is what? V, right? Its initial velocity is v. It's v, right? Which is basically our unknown in this case. Which is basically our unknown. Now, from what I have, the equation that I'm going to choose is VF, V final equals V initial plus AT, right? Now, what is our V final? Our V final is 3V, right? 3V equals V. Our V initial, they said it's V, plus our acceleration (9.8), and then at the time of 1.2 seconds, right? So if you punch this in your calculator, you'll get v minus 11.8, and then we take this v to the other side, we will get 2v equals minus 11.8. You divide both sides by 2, you'll get your initial velocity. Remember, in the space of v initial we have v, so from here you can simply go back to v initial and say your v initial is negative 5.9 meters per second. 5.9 meters per second. Now as the stone leaves the hand of whoever threw it, it leaves the hand at the speed of negative 5.9 meters per second, which is 5.9 meters per second towards the ground or downwards. Now moving on to the next question. Now here it's a statement first. It says, at an instant the stone passes its initial position on its way down, stone B hits the ground, right? Now they want us to calculate what? The height. They want us to calculate the height, right? What do we know about stone A and stone B, right? Now let's understand the question first. At an instant stone A passes its initial position on its way down, stone B hits the ground, right? So let me just try to illustrate that for you, right? Let me just try to illustrate that for you. Now at the initial position, right, it goes up, right? And then they say as it passes its initial position, which is here, right? This is stone A. This is stone A, right? As it passes its initial position, stone B, which was thrown downwards, it hits the ground. As stone A passes this point here, this one hits the ground, right? Now what do we know about stone A? Let's start with time, right? It took it 1.2 seconds to reach its what? Maximum height. To reach its maximum height. 1.2 seconds, right? So we can say at 1.2 seconds, as it reaches its maximum height, stone A is somewhere halfway, right? But as it moves down and passes this initial height, remember time symmetry, right? As stone A passes this, how long did it take it to pass that point? We are going to say it's 1.2 times 2, right? Because double the time, right? The amount of time it took it to go up, and the amount of time it takes that stone to pass this initial position is double the time, which is 2,4 seconds, right? Now in this 2,4 seconds, that's when stone B hits the ground, right? So basically we know the time that it took stone B to hit the ground, right? So we can say our time for stone B is 2,4 seconds, right? We can say it's 2,4 seconds. And then remember we calculated its initial velocity at negative 5.9 meters per second, right? And then we know our acceleration due to gravity, which is negative 9.8 meters per second squared, right? What do we have? Now we have our three variables. We can find our own unknown, which is the what? Which is the height. Right? Now which equation are we going to choose from here? Let's go with change in x equals v initial times t plus half a t squared, right? What's my v initial? My v initial is minus 5.9 it's minus 5.9, and then my time is 2,4 plus half times negative 9.8 times 2.4 squared, right? Now if you punch this in your calculator, the first one you're going to get negative 14.2 minus 28.2. If you add those two together, you will get negative 42.4 meters. You will get 42.4 meters. That is the height of our building, right? Now the next question, 3.4. They say sketch velocity time graph for complete motions of stone A and stone B on the same set of axes. Label your graphs stone A and stone B clearly. Show the following graphs. The time taken for stone A to reach the maximum height and the velocity with which stone B is thrown downwards. Meaning we are going to have the velocity time graph. So let's quickly plot our graph. Let's quickly plot our graph. See, let me start by this. right? This is the velocity, which is in meters per second. This is velocity in meters per second. Alright guys, then this is here, this is time, which is in seconds. Now let's start with stone A. Let's start with stone A. We know the initial velocity of stone A to be 12 meters per second, right? Which I will just put over here. Let me just increase my, I'll say this is 12 meters per second. And then we know stone B to be 5.9 meters per second. Now, why do I plot stone B here? Remember, it's positive 12 meters per second because it starts to go down, right? It's thrown up, it's thrown up, and then it's gonna start going down, right? And then stone B, it starts from being thrown straight down, which is 5.9, right? 5.9, right? And then let me plot the time. The time it took stone B to go up and down. So let me, before I plot that, let me label my time here. Let me say here it's 1.2, and then here it's 2.4, right? It's 1.2 and 2.4. Oopsie. Here is 1.2, here is 2.4. All right, so my stone B starts here at 12 meters per second, and then after 1.2 seconds, it reaches its maximum height, and then it stops. Can you see the velocity here is 0? It stops and then starts moving down, right? But my stone B is thrown straight down at the initial speed of 5.9 seconds, right? So let's plot our graph. Let's see what we have if we plot our graph. We will have stone B, stone A, and then here we will have stone B. This is stone A, this is stone B. And then remember, at some point after 2.4 seconds, stone B hits the ground. So this is, again, this is a rough sketch, but if you guys can notice here, these lines should be parallel to each other, right? If you draw it according to scale, you will get perfectly parallel lines, right? If you draw it according to scale, you will get nice parallel lines. But that's the graph of stone B and stone A. All right, let's move on to our last question, our last example, which comes from 2019 paper. Again, I think it's the June one. Let me check. Yeah, it's June paper, June 2019. Let's go through the question. It says a ball is thrown vertically upwards with velocity v from the edge of the roof of a 40-meter tall building. The ball takes 1.53 seconds to reach its maximum height. Ignore air resistance. Now, I'm not going to define free fall. It's all in your textbook. I'm going to get right into the calculations, which starts at 3.2. Now it says calculate the magnitude of the initial velocity v of the ball. Now, what do we know? Again, let's start with what is known. We know our A will be negative 9.8 meters per second squared. We know our time, which is 1.53 seconds, and then we know the V final, which is 0 meters per second, right? Let's read the statement again. The ball is thrown vertically upwards with the velocity of v from the edge of the roof of a 40-meter tall building. The ball takes 1.53 seconds to reach its maximum height. Ignore air resistance. And then they want us to calculate the initial velocity, right? So we have our three known variables. So I'm gonna go with V final equals V initial times AT, right? What's our V final? Our V final is 0, and then our V final is 0, and then we are looking for our final velocity plus negative 9.8 times 1.53. If you multiply that and then take it over to the other side, our initial velocity would be 15 meters per second, right? Now, before I forget, guys, what did I miss here? what can you tell me that I missed by mistake? I forgot to show my direction. So I'm gonna choose up. I'm gonna choose up as positive. Up is gonna be positive. All right, let's move to the next part of the question. It says you must also calculate the maximum height reached by the ball above the edge of the roof, right above the edge of the roof. Again, our variables, what do we know? Now what is known is initial velocity, which we just calculated at, and then we got 15 meters per second. We also know our final velocity at 0 meters per second. We also know our A, which is 9.8 meters per second squared. Now on this one, I'm gonna go with V final squared, V initial squared equals V initial squared plus 2A times a change in displacement, right? What's my V final? My V final is 0. My V initial is 15 plus 2 times 9.8. What am I looking for? I'm looking for change in displacement. Oh, remember here it's squared, so I'm gonna get 225 squared plus 2 times negative 9.8 times the change in displacement. I'm going to take the 225 to the other side and then divide by the product of what I get here, and then my change in displacement would give me 11,5 meters. 11,5 meters. That's our answer. Now 3.3, it says take the edge of the roof as the reference point, right? Determine the position of the ball relative to the edge of the roof after 4 seconds. After 4 seconds. So how do we go about in calculating that one? They just want us to calculate the position of the ball relative to the edge of the roof after 4 seconds. Now let me just try to draw it down. Now the ball goes up, and then remember it's thrown from the edge, right? This is my edge. This is my edge, right? Now it comes down. Let me just redraw. This is my edge, right? It goes up, it comes down. Now what they want us to calculate is the time. What they want us to calculate is actually the position relative to the edge. Like I said, this is my edge. Relative to the edge is right in line, right in line. And then they say it's 4 seconds for the ball to reach that position, which is relative to the edge. It's 4 seconds. Now what are they looking for? They are looking for this height here. They are looking for this height here. This height here. That is what they are looking for. They are looking for this height. They are looking for that height over there. Right? Now let's calculate that height over there and see what we get. I'm going to start a new slide. This question is question 3.3, right? It's 3.3. 3.3. Right? Now what do we know? We know the time. They gave us as 4 seconds, right? We know the initial velocity of that ball, which is 15 meters per second. What do we know? We know the gravitational pull, which is negative 9.8 meters per second squared. Right? All right, let's get calculating. What I will go for here is change in displacement equals v initial times t plus half a t squared. Half a t squared. Right? What's my v initial? My v initial is 15 times my time, which is 4, plus half times negative 9.8 times the time, which is 4 squared. Right? So if you multiply that and then you solve that, you will get 60 over here minus 78.4. What will be your final answer? Your final answer will be negative 60 minus 78.4 will be negative 18.4, which is downwards. Right? Like I said, let's just rewrite it again quickly and try to get a picture of what we are dealing with. This height here is what? It's 40 meters. Right? What did we just calculate? The height relative to the edge from where the ball was thrown, right? We just calculated this height here. Right? As it goes up and then it's gonna come down. Now this height here we just learned is 18.4, right? 18.4. Let's move to the last part of this session. They say, let's look at 3.4. They say, will any of the answers to question 3.2 and 3.3 change if the height of the building is 30 meters? Choose yes or no and give a reason, right? Now what did we calculate in 3.2? 3.2, we calculated the height and the velocity, and in 3.3 3 we calculated again the height or the position, right? Now they say from here, they say you make the height less, you decrease the height, right? Now will any of the answers to question 3 and 3, 3.2 and 3.3 change the height? Will any, let me just read it. Will any of the answers to question 3.2 and 3.3 change? All right, let's look at that. Let's look at 3.3. Let's look at 3.3. Will this change? I don't think it will, because look at the height, which is 8.4 meters, 8.4 meters, and they say they changed the height to 30 meters. Now will it have any bearing here? No, because this height is less than the 30 meters which they say they have changed it to. What will happen here? The ball will still be in the air. So no, nothing will change. The ball will still be in the air. If they decrease from 40 to 30, the ball will still be in the air. Unless they said it was less than 8.4, it would have hit the ground anyway. But then at 30 meters, the ball will still be in the air. So no, nothing will change. Let's look at 3.3. Is it this one? Let me just go back. All right. Seems like my slides don't want to come up, but anyhow, will anything change from there? Like I said in that 3.3, nothing will change. We had 18.4 meters, which is still above the edge, right? And they only took out 10 meters from that building which the ball was thrown from. So will that change? No, it won't change. The ball will still be in the air because the difference is way too much, right? It's way too much. It's 30 meters, it's 18 meters. So the ball will still be falling down, right? Again, at 3.2, the maximum height reached, we calculated the maximum height reached by the ball, right? At 3.2. And from that height, what did you get? We got 11.5, right? What does that tell you? The ball would still be in the air. So no, nothing will change. If they change the height to 30 meters, nothing's going to change because the height will still be in the air. And in terms of velocity, again, the velocity would, in this case, the velocity would be constant. So nothing's going to change because they started at 40 meters, right? And then what we got 11.8. They started at 40, and then they made they decreased the height of the building, right? It doesn't matter because we got less height that we've just calculated. So the ball will still be falling in that manner, right? So that would be my answer. No, it won't change anything because the ball would still be in the air. That brings us to our last session. That brings us to the end of this segment, and I hope you guys enjoyed it, and I'm looking forward to our next lesson. And yeah, enjoy. Thank you.